All right, we're going to take a look at this optimization problem where we have a cylindrical paint can that needs to contain 4 liters of paint. And we need to know what dimensions we should use in order to minimize the amount of metal used in the making of the can. So what we're doing is we have the volume has to be fixed. At 4 liters. And we're supposed to minimize, if you think about what needs to be minimized here in terms of the geometry, you're minimizing the amount of metal used. So that's just a thin sheet around the surface of the can. So that really is the surface area of the can. Now thinking about how that is going to be played out, we have we need to know what the formulas are for volume and surface area. So let's look at the volume. That's going to be the area of the base times the height for any cylindrical sort of solid. So area of base is pi r squared and times the height. Now, of course, we should also be thinking about the units here. Both R and H are going to be in length measurements. Right? So that means they might be measured in centimeters or inches or maybe feet or meters or maybe miles. There's lots of different length measurements. And thinking about the likelihood of any one of these, there's only one measurement that is given in the statement of this problem. And that is in this 4 liters. So liters is a metric measurement. So that tells us that we can't be in inches or feet or miles. Now, thinking about centimeters versus meters, if you know how big a centimeter is about the width of your pinky, and a meter is about the length of a baseball bat. So we are not going to be measuring the dimensions of a paint can in meters. So it's most likely going to be centimeters. So now if we have R and H in centimeters, then I'm squaring the radius and then multiplying by the height, then the volume would be in centimeters cubed or cubic centimeters. Okay. But this says that the volume has to be fixed at liters, 4 liters. So how do we resolve that? We need to have some sort of a relationship between liters and centimeters. And there is actually a pretty simple relationship if you know it. So 1 liter is, do you know how many milliliters there are in 1 liter? Metric system says milli is 1/1000th. So 1 liter is 1,000 milliliters. And 1 milliliter, that's a small amount of liquid. That's the same as 1 cubic centimeter. So cubic centimeter is a little piece. It's like, imagine a cube that is 1 centimeter by 1 centimeter by 1 centimeter. And if you have that cube that is made out of water, it goes sploosh, and that is 1 milliliter. So milliliters and liters are typically used for measuring liquids, and cubic centimeters and cubic meters are more often used for talking about the volumes of solids, or of air. but that's the conversion. So 1 cubic centimeter is the same as 1 milliliter. So that tells us that the volume of 4 liters, that's the same as 4,000 milliliters, which is the same thing as 4,000 cubic centimeters. So now our problem is we need to figure out what the surface area is. We need to minimize the surface area with a fixed volume of 4 liters. So that means, so the volume is, this is pi r squared. H has to be equal to 4,000. And that's going to be cubic centimeters. Surface area. How do we figure out surface area? If I have a cylindrical can and I want to figure out the area of all of the metal in the can, then I could imagine, I think if I was to figure out the area of the metal, I would probably snip off the 2 ends. I would have 2 circular pieces, right? So each one is pi r squared. And then there's 2 of those. And then the side surface, you can imagine cutting this down the middle and opening it up. And when you do that, you're going to end up with a rectangle, right? So what's the rectangle? Let's see, the height of the rectangle is going to be the same as the height of the cylinder. And the width of the rectangle, let's put the R here. The width of the rectangle is really, if you think about it, that's going to be the circumference of the circle, which is 2 pi r. So that tells us that the area of the rectangle is going to be 2 pi r. That's the base length times the height. So now the total surface area is, I'm going to have 2 copies of that circle where each one is area pi r squared. And then the rectangle is 2 pi rh. All right. Now this area depends on 2 variables, right? I have an r and I have an h. So this is where we use the fact that the volume has to be fixed at 4,000 cubic centimeters. So that means we could actually substitute for one of these variables. We could solve that equation for one of those variables and substitute it into the other equation. And I don't know about you, but I think in this case, it looks like it's much easier to solve for h than it is for r. So I'm going to take this and I'm going to solve for h. H is 4,000 divided by pi r squared. And I'm going to take that and substitute it in for the h there. So now my area is 2 pi r squared plus 2 pi r times h is 4,000 over pi r squared. And now this area is a function of r, only one variable. So now what we can do is we can minimize that. And we're going to find r to minimize this function using our standard calculus tools. All right. Now, I want you to recognize that a lot of the mental work that we have that goes into this problem is already in is just in setting it up and figuring out how these statements of this physical problem can be translated into math. Okay, so this is the bulk of the work. And now we're kind of going through the motions of, I know how to maximize and minimize a function. It is like I take the derivative and find where the derivative is equal to 0 or where the derivative is undefined. Okay. So let's go ahead, and I want to simplify this a little bit before I take the derivative. It looks like here I have a common factor of pi, and I also have a common factor of r. So I'm going to rewrite this. A of r equals 2 pi r squared plus, looks like 8,000 over r. I'm going to find the derivative. So a prime of r is going to be 4 pi r minus 8,000 over r squared. So remember the derivative with respect to x of 1 over x. This is the same as x to the minus 1. That's -1 times x to the minus 2, right? So that's where I get the negative there and the 2 exponent. All right. So now we set a prime equals 0. So we need 4 pi r minus 8,000 over r squared equals 0. And I'm going to multiply both sides by r squared in order to clear that denominator. So that's 4 pi r cubed minus 8,000 equals 0, which tells me r cubed equals 8,000 divided by 4 pi. I don't know why I can't see both pages at the same time. R cubed equals 8,000 over 4 pi. So I have a common factor of 4 that I can cancel out. So it's 2,000 over pi, right? 4,000 over 8 pi, or sorry, 4,000 over 8,000 over 4 pi, 8,000 over 4 pi. Okay, so taking the cube root, r equals cube root of 2,000 over pi. I know that I have a 10 cubed in there is 1,000, so that's the same as 10 times the cube root of 2 over pi. Now, I want to take this and I'm going to double check using some technology real quick. Okay, so I have this graph. I graphed that original A of R. And one of the things that I noticed about this, the graph isn't showing up. I don't even know where it is. So, oh, there's something there. There's part of the graph. And maybe if I zoom way out, then I might be able to see something. But instead of doing that, I think what I'm going to do is I'm going to get some sort of an idea of what's going on. So I got r equals 10, what was it, 10 times the cube root of 2 over pi. And instead of the cube root, I'm going to use to the 1/3 power. So 2 over pi to the 1/3 power. Okay, so that tells me that the minimum should be happening right around 8.6. So I want to know what is a of that number. So if the minimum is around 1400, that tells me why I'm not seeing this graph on the screen. And the minimum is right around 8. So I'm just going to go ahead and change the y coordinates of my viewing window. And I want to go up to, if this is the minimum at 1400, I'm going to say what happens if I just go up to 2400. There we go. And maybe I want to even go up to 3000 just to bring that graph a little bit more into view. Okay, so that tells me that this gives me a little bit better of a view of the function that I'm looking at. And now I can kind of zoom out and see a little bit more of that function. And it does look like I have a minimum at around 8-ish. So if I click on the graph, then that actually highlights the minimum. And looky there, it gives me exactly those numbers, the coordinates of 10 times the cube root of 2 over pi is the same decimal approximation, it looks like, and the output value is the same up to 3 decimal places. So I feel pretty good about that as an answer. I just wanted to point out you can also use Wolfram Alpha is another place where you might look. So I just put in a of r equals, and I didn't actually ask it to do anything. I just said, tell me something about this function. And it gives me a couple of graphs of this function. It chose some graphing ranges, which may or may not be helpful graphing ranges. But here, you can't really see that there's a minimum there. Here, you kind of can, but like it's, I think that these are not really the best graphing ranges. I like having manual control. But, notice that we used calculus to figure out what is a good graphing range here too. So it gives a couple of alternate forms, rewriting it with a common denominator. Alternate form assuming r is positive, okay. It has a real root. Real root is a negative number, and we see, here it is at where r is a negative number. And I really don't care about that negative real root because that is irrelevant in the case where, we're talking about a paint can. R is a positive number. Complex roots, I don't care about these things. This is the derivative, and I can look back on my work and see, yes, that's the derivative I got. Look, there's a local minimum. And it says there's a local minimum at 10 times the cube root of 2 over pi, which is exactly what we got. So there's a couple of checks on technology to see that we're kind of getting the same result. Now, I want to go back to the writing here because we haven't actually solved it. The question was find the dimensions in order to minimize the amount of metal. Okay, so we found r, we need to find h. And somewhere around here, we had h is 4000 over pi r squared. So h equals 4000 over pi r squared. So plugging in that 4000 over pi times 10 cube root of 2 over pi all squared. So let's see, 4,000 over pi. 10 squared is 100. And we have cube root of 4. Or maybe I'm going to do this. I'm going to do 2 to the 2/3 over pi to the 2/3. And one of the things that allows me to do, I can cancel a factor of 100. And I can also say that pi to the 2/3 cancels with this pi. This is pi to the 3/3. So that means I'm going to cancel those, and I'm going to be left with pi to the 1/3. So it would be 40 over, it would be pi to the 1/3 times 2 to the 2/3. And I think what I'm going to do is 40 over, I'm going to say this is the cube root of 4 pi. And I'm going to go ahead and use a calculator or Desmos to look at this. My R was 10 times 2 over pi to the 1/3, and that is approximately 8.60. And the H, I'm going to write H equals, what is it? 4,000 over pi r squared. I'm using the capital R, so I'm using that. And I also want to double check with the calculation that I did, which is 40 divided by the cube root of 4 pi. And it looks like those two numbers are approximately the same. So this is approximately 17.21. So this says the answer is the can should have radius about 8.60 centimeters and height of about 17.21 centimeters. So that is the work that we did to optimize. Again, just kind of going back, the big work was actually getting this into the mathematical context. We had to know some formulas for volume and surface area. We also had to know some conversion between cubic centimeters and liters. And then we had our thing is we were minimizing the area subject to a fixed volume, right? And then that allowed us to get one function that was just written with one variable in order to minimize that using the derivative. Worked through that. We actually used technology to double check our algebraic work. And we eventually come through and get the dimensions of the optimal size can in order to minimize the surface area for that volume.